Hello! ASIC design is in a place similar to where the internet was a couple of decades ago. Suddenly, it's opened up wide and now accessible to us all. It's fun and powerful and still a little rough around the edges. And this is a great time to get involved. Now, digital design is super powerful, and if you want to make the next Bitcoin miner or something, you can do that. I've done a few digital projects, but I've finally started getting down to really sculpting atomic structures and changing how I think about electronics and circuits, thanks to the new analog capabilities afforded by Tiny Tapeout. So I want to introduce you to what it's like doing analog and mixed signal designs using completely free and open source tools. If you've done circuit and PCB design, the steps are roughly the same and familiar. You design to meet your specs using xschem rather than KiCad-E schema, and I'll talk about why, but it's just schematic capture, right? Then use magic rather than, say, PCB-new to do physical layout. Okay, but it's like moving to a foreign country where you speak and read the language. Some of the rules and customs are different, okay. But for a little while at the beginning, it's the being sporadically slapped in the face by surprising twists that can be jarring and tough. Hopefully, this tour will minimize the culture shock for you. Here I'll go over all the steps and give a crash course on everything. You won't get to mastery within 20 minutes, but I will go through every procedure that got me from an empty page to a working analog to digital converter, so you'll get a good taste of what the process is like, and I'll touch on how stuff works as we go, so hopefully you pick up some insights and maybe a few tricks along the way. Now, analog ASIC design could be a semester-length course that I'm not yet qualified to deliver, but I will give you a nice sampling of the process of doing a full mixed signal design using tools you can get into your computer right now. No cost, no NDA, no trouble. So why analog? Because it's fun? Well, seriously, digital lets us forget the messiness of everything and think in terms of bits, and it's super powerful. It's really cool, but there are two downsides to restricting ourselves to digital. It's a bit opaque, at least for me. The generated circuits are so involved that your mind just goes, ugh. You can poke around, but you skip over lots of it and never really see the entire picture. The machines make all the low-level decisions, and you're just a consumer. So you stay clueless to the choices and trade-offs that are made in your name. And the world ain't digital, at least on the human scale. Every time you question the universe, the answer is going to be yes, no, and very often something in between. Anytime you want to interact with that universe, whether it's by tugging on the EM field to send radio waves, or even if you'd rather forget about all the fuzziness and send digital signals, you're always bumping up against the analoginess of everything. Yeah, I'm sure that's a word. So I think it's good to play with, even if, in the future, you'll only be doing digital designs. The experiences will inform your decisions a whole lot. Now, by getting over the bump of starting to understand how every choice has impact and is a trade-off, and with which things, your intuition for how stuff works and how to build circuits develops like crazy. But on top of all that, many of the coolest and toughest things happen in analog, and it's often the analog side that determines a system's ultimate performance, so there's plenty of room to get good at stuff, make cool things, and rake in the big bucks if that's what you'd like. Now, I'm a digital boy, and so I jumped in through the question, how do we bring state information from the analog world into our digital machines? The answer to that was my first try at an analog ASIC, and it's a mixed signal design, an ADC that touches a voltage in the world with an analog front end and then uses logic to translate it to an 8-bit number that can be used in compute specifications. Because a big part of this process is manual and one way, it's pretty annoying to change a layout once it's done, it's a great idea to sit down and have a hard think about the requirements and objectives to come up with precise goals and specifications before you start. That is smart and not at all what I did. I've done some analog, but it's not where I shine brightest, and to avoid confronting the learning curves of both the tooling and the analog world at once, I started by getting everything installed using a super practical virtual machine that has everything you need. Then, with no clue, experience, or plan, I turned to the experts and started following along with a walkthrough that Matt did with Stefan Schippers. Stefan has a quarter-century of experience in VLSI and is the creator and maintainer of xschem. In that video, Stefan actually did all the hard work of designing a sensitive comparator and does a great job of walking through how he uses xschem to build it up and then look at it using simulation. Schematic capture. There are a few reasons to use xschem, mainly because it's super well designed for just this type of work and has really good support for the open Sky130 PDK we're using. To actually learn and get used to xschem, in the VM, on my own copy of the program, I slowly followed along, building up the same circuit, one component at a time. There are a few things to say about xschem, and the software we'll be using in general. First off, they are old. Well, actually, no, they look old, and some of them began long ago, like Magic is from the 80s or something, but they're alive and well and in development right now. The thing is, they have history and a look and a way of working that might be pretty alien and surprising to you. They sure were to me. At the last Latch Up conference with Tim Edwards, who maintains Magic, in attendance, I said to him,
and then I used Magic. and magic was, let's call it a learning curve. It's good we didn't meet a week ago, because the principle of least astonishment, no, this was astonishing. I actually turned it off once just because I didn't know how to get out of this mode with my mouse. I felt like my grandmother.
Yes, lots of it can be astonishing. That's great when I'm watching a movie, but astonishment is something I don't usually want to feel when I'm in flow trying to get stuff done. So part of the process for me was deciding what to learn and what to tweak to my liking. As you may know from my previous videos, I'm a little obsessed with keeping my hands in place. Right on the mouse, left with easy access to operations I use constantly. So I quickly decided to leverage my muscle memory and remap certain operations to match what I already use in KiCad. The good news, both xschem and magic are crazy customizable. You can change or script pretty much anything pretty easily. Okay, the bad news. Both xschem and magic use Tickle. TCL, the tool command language, and I'm not too ticklish. Tickle is an old-school scripting language, one that apparently originated inside of Magic itself and then grew up to become a standalone programming language. It has a bit of weird, but is really easy to pick up, and you can do anything you want. Anyways, as I followed along, I got a good idea of all the things you need to do and how to do them, as I was tailoring the experience to my own taste. I'll make a video focused on each of these tools and get into all of this further, but here's the 10-second crash course for xschem and schematic capture. You design a circuit using components and wire them together. Normal stuff. The components you use come from the Skywater PDK. In theory, you could actually get down there and even draw your own MOSFETs, but there are tons of design rules to obey, and people with great expertise and inside knowledge of the process have dealt with lots of that for you, so you're best off just customizing existing cells. The things you can count on in PCB land, like getting a resistor of a specific value, no. Same for the range of available components. What you have to play with is both limited and kind of tricky. First off, did you notice anything about that circuit Stefan was making? Yeah, it's a bunch of FETs. Wired up in some weirdo analog way, current mirrors, all that stuff. But you see FETs, bunch of FETs, mostly nothing but FETs. Here we're in the world of the tiny and the rules are different. Everything's optimized for making MOSFETs and you're going to do a lot of that. So you can create a lot of different kinds of those, and used intelligently, your circuit will behave well without consuming much power, which is what CMOS is all about. When you open up xschem in the VM, you get a nice overview of everything in the Skywater PDK, the process we're using to make these chips. Now there are lots of examples to look at, and they are very helpful, but check out the components there. That's everything available, and what do you see? FETs. Now resistors are pretty easy too, and there are choices there, but the thing to remember is you're not going to get 1% precision here, or even 5%. The precise values of all the components are fuzzy, like really fuzzy. On top of the effect of what's around them impacting etching and implantation, inherent nonlinearities like voltage dependence, and more inside of a single die, on top of all that, there can be a 30% difference between the different runs of the exact same masks. You'll get chips with vastly different absolute values from different wafers. So lots of the technique is to expect rough values and instead leverage ratios. Two resistors you create with the same physical properties close together in the same environment may be 1,000 ohms or 1,100, but they'll match pretty well between themselves. So if you stack them to make a voltage divider, the output will be 1/2 VDD, regardless of the precise value. And this is something that comes up a lot. Using ratios in designing your circuits rather than absolute values, and using placement and other tricks to make sure the matching between different bits is good, meaning these two things are about equal, this thing is about 1/2 this other thing, whatever. Other than FETs and resistors, capacitors are something you can have too, but they come at a huge price. Lots of area for very little capacitance. And check this out. This is a new design by Devin Atkin for TT07. Notice that fat rectangle top right? That thing taking up 1/4 of the space in there is a hefty 0.5 picofarad capacitor. You get more capacitance from traces on your PCB. So you can, and I have, used capacitors, but they'll take up space and yet be small. Finally, there are a few other things in there. Diodes, one of each type of bipolar transistor, whatever. Mostly you use FETs and maybe some R and C. Now don't even think about inductors. For now at least, just don't. Let's actually make a simple thing. That way we can look at the customizing I mentioned. Now there's a sweet talk by Harold Prettel, 50 nifty variations of 2 transistor circuits. These are a whole bunch of ways of using just 2 MOSFETs. I'm curious about radio stuff, so let's make the dual gate MOSFET mixer on the bottom right there. Now, it's not a good mixer, but look how simple it is. Now, we want a new circuit, so let's save that, and I'll just call it mixer. Okay, so we want the pins. Now, when I'm in xschem here, I can add stuff, and you could add your own stuff, but you could also add stuff from the xschem library. This is basically spice stuff, meta stuff, things that don't exist, not real components or anything like that. So I want a label or a pin. So I want an input pin, so I'm going to do that. Actually, we're going to create a few of these. So let's see, boop. Now, double clicking opens this up. You could also use Q. I'm going to do LO, and then I want to copy that. I have an RF, and we're going to add one for the VSS, the ground we're going to tie on the low side. And finally, we have our output. Now, I could go and fetch it, but all I have to do is change this to an O pin and then call it I out. There we go. So we have our 4 pins. Now it's time to add the MOSFET. This will be in the Sky130 libs tech blah, blah, blah. These are the actual components, the standard cells. So you can see we have caps, a whole bunch of FETs, and resistors. So let's take a regular NFET, just a 1V8 here, and add this. Okay. So this guy, well, we actually need 2, so I'm going to copy that. Okay, and you can see you can edit this thing, and it has a bunch of parameters, stuff you don't want to touch and stuff you do want to touch. I mentioned customizing. There are a few components, but they are highly parameterized. They have parameters. So I've added a basic NFET. Now a MOSFET has a drain and a source, which you can think of like conductors, separated by a gap that can act something like a variable resistor. You control the value of that resistance with the gate. Okay, fine, yeah, a MOSFET, we got it. The 2 fundamental tweaks you can make to this arrangement when you're down here in the weeds of physical devices are the MOSFET width and length. Let's see from the top. Now the width I think of as how many electrons can stand shoulder to shoulder waiting to be allowed to cross the gap. A bigger width, more electrons, so current through the FET will go up with increasing width. The length is the channel length. How big a gap the charge carriers have to cross to get between source and drain. Now this channel is the variable resistor part. It's not like metal. It's a place where electrons just drift around, bumping into stuff, and are generally pulled in the direction by the potential difference between the source and the drain. The speed goes up with that voltage and the VGS for a while, but it basically tops out pretty quick. Now the longer they need to get across, the longer before the next guys in line can jump in the pool and swim across too. So bigger length equals less current. In the end, it's all super complicated, and there are a bunch of effects to consider, especially as you get smaller. But with other things being equal, to a first order, you can think of current through a FET being proportional to width over length. So those values will impact your gain, your output resistance, all the stuff you actually care about. They get set by these 2 things that you can tweak. So you'll see lots of stuff about W and L and spend a lot of time thinking about how to set those during design. Now, I didn't know nothing about that stuff at the time, so I let Stefan do all the work for me with my first comparator, and here we'll just leave it to the default minimum length of 150 nanometers and a width of 1 micron.
So on top of the length and width, you can also play with the number of fingers here and the multiplicity, but I'm just going to leave that as is for now. But I did actually do a test. Let's take a look at that. So here we can see that I've got a bunch of FETs. I've got this one, that's a regular just NFET. This is my reference, it's a 1x1. And then I've got this one, that's 2 times the width. And then I've got one with 2 fingers, and I've got one with multiplicity 2. And then I did a bunch of sweeps at various VGS. Now let's just take one. If you look at that, you can see that the 2-finger and the single standard reference FET, they're basically the same, whereas the multiplicity and the 2 times wider, they're not quite the same. Anyways, the point is, in this case, we're just going to leave the FETs as is, but there's lots to play with here. So time to wire it up. I'm just going to move these things and set them up. And wire VSS. Boop. Boop. There we go. Perfect.
I've got my little circuit, and we could move to layout, but does it even work? It's time for a layover at Simulation Station. Simulation. Even if it's not costing us $250,000 to make these anymore, when the time between submitting your design and having it in your hands is 7 months or something, you realize it'd be nice to get decent results on the first try if possible. So there's lots of simulation involved at multiple stages. 3 bits of great news are: this isn't so hard, and it really helps to understand and tweak circuits. Xschem is very well designed to help you integrate simulation into your files and flow. And xschem and Sky130 work with ngspice, just like KiCad, so skills developed in one easily translate to the other. What you get good at in ASIC land will be mighty useful when making PCBs. Now, just like all these tools, ngspice has a history and quirks, but wow, this thing is powerful and useful. Twice I've started making a KiCad ngspice video and never published it. Now it will be an ngspice for PCB and ASIC video, but I will get it done and out with much more detail.
I've got it all wired up. Now it's time to test it. So what we're going to do is just create a symbol from this thing. And this is pretty damn easy. All you have to do is make symbol from schematic. Yeah, I would like that. Okay, it's done. And now I could actually open that up. Current year. There we go. The .sim was created. It's kind of ugly. I'll fix it up a bit and create a test bench for this guy. Okay, I've got a little test bench here, nothing too complicated. This is my symbol. You can always enter a symbol and see that it's fits under the hood. And basically I'm feeding it an LO and RF through SPICE stuff, just 2 sine waves, one at 15 meg and the other at 12, so 3 megahertz apart. And then I tied VSS to ground and have some pull-up resistor or whatever just to see some output. Now the SPICE itself is this stuff. And I won't get into it in this video, but basically it's ngspice. And what I'm doing is basically running at various LO bias voltages. So I'm going to try one, just go up. So once you have your SPICE set up and all this ready, all you have to do, click netlist. Okay, that generated the netlist. Now, if you want to see it, you can always have a look at it. So let's see, edit netlist, boop. And there it just made a bunch of SPICE. Here's my bits, and there's other bits, and there's just a bunch of bits. So let's simulate it. Now it opens up this little window, runs ngspice, does all the tests, and it spit it out. Now, one of the things I did here was I created an output file, and I'm going to load it, and here we go. So this is all the runs. And you can tell that, okay, so when the bias is low, this is low, and you don't get much action. But when the bias is high, let's try this one. Okay, let's see. This is my input frequency, the RF or something, at 12 megahertz. Here's the 15. And what do you see? Oh, down at 3, here's the difference. And up at 27, that's the sum. Pretty cool. Now, what you can tell is that with a low bias, it sucks like terribly. But up here, let's say, yeah, that's pretty good. So a bias of about 1 volt, and we're golden. So that's what the test bench is for. You get to know your circuit a little. You know that it works, and everything is beautiful. And these graphs make it really pretty nice to look at too. For a more complete example, check this out. This is the comparator I did based on Stefan's work. So, okay, cool. That I made a symbol from, and let's go up a level. It became part of the calibrated comparator. Now, this is a comparator, but it also has switches and a mux to be able to do calibration. Okay, up a level. Oh, this was part of a bigger system. So the calibrated comparator also interacts with an R2R and another mux, and that way we have a SAR ADC. And finally, up a level here, and this is my final test bench for this guy. So this is the circuit we were just going down and up, and this is basically the parasitic extraction version. So if I load the results of this test, okay, it doesn't really matter what this says, but in essence, it was working. So if you want to see something really interesting, at the end, I did the whole system. So this is basically a parasitic extraction of the whole thing, everything I ended up doing. And if you load the waves here, oh, this is everything. It took hours and hours to do. But in essence, I'm setting a voltage on the input, let's say this one, and here's what the DAC does. It calibrates and then it says, oh, the signal is higher than me. Okay, so that's, let's say, that's here. The signal is higher than me. So, okay, I'll go up. Oh, the signal is lower than me. I'll go down, 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 and I finally get a result. And here it is. The answer, of course, is 42. So, whoops. So these are all the runs, and basically I can look at any one. And the interesting thing is that it works pretty darn well up to a certain point. After a certain level, the comparator goes nuts. And then it just keeps thinking up, 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 and the answer is way too high. So I took this, and this is a really nice interface, and I ended up taking all that, investigating through there, and I also did a summary of all the results with this. So here's the DAC output in general, and here's a sample. But the point is this. By saying, okay, I expect the answer to be hex 10, well, it turned out it was 11. It came out 11 in the sims. I expect 20, 20, 30, 31, 40, 42. So pretty good. That's going to be awesome. And this gives you an idea of the kind of reports you could make with xschem and ngspice. It's pretty amazing. So the answers match the expected up to a certain point, and then things go really badly around here. So CO, C6, that's pretty good. And then, ah, well, better luck next time. But for my first mixed signal design, I'm pretty happy. And these test benches are insanely cool. I wound up simulating the entire thing, both analog and digital sides, down as individual analog transistors along with the parasitics. Let me tell you, that simulation took a while to run, but the results are really cool. Okay, I'm getting ahead of myself with parasitics and all that. Say we're happy with the simulation and ready to do some layout using Magic. Getting started is pretty easy, but I have to tell you, if you're not some graybeard who's been working with this stuff since the 90s, Magic isn't some gentle culture shock. Here you really are, for a little while, a stranger in a strange land. Now, I sound like I'm griping. I'm not. I actually have come to like Magic a lot. I'm amazed at what it can do. I love how it warns you about breaking design rules in real time. I find it awesome how it can create spice models, including parasitics, from just drawings of rectangles on layers. And I really like the way it works, at least after a good deal of tweaking. Now, Magic is really friendly to customization from the bottom up, and it's made to make you effective. You can use it mostly with just a mouse, clickety-clicking, but you get crazy efficient when you combine that with the console, and that fits right in with my way of doing things. In Magic, you're basically always using, other than your beautiful mind, 4 tools: the mouse pointer, the console, the DRC status, and the box. You keep an eye on design rule status, use mouse and console to take actions, and the box basically decides where these actions take effect. What you're doing most of the time is just filling rectangles with colors. It's just like using paint, except that your color choices turn the little squares into functional devices. So let's have a look. Okay, let's get back to our mixer. I'm going to launch Magic here. I've got a little shortcut that gives me a Magic with a Sky all set up, and you can tell that there with the Technology Sky 130A. So this is Magic. Okay, let's grow this window a little. Okay, so this is Magic. I'll get rid of the grid here, and in essence, here's the box, and you can control the box and move the box. Here's my mouse. This is the DRC up here, and if I do something terribly wrong, like say I do a tiny box here, a tinier box. The grid. Okay, so give me a tiny box and I will paint it with M1. DRC. So I can ask DRC why, and it'll tell me, oh, the metal is, it's too small. This is too small a square. I can't make this. Anyways, so Magic is pretty interesting. You can use these things with the console down there, and that's what I end up doing most of the time. But you can also use these things and basically click stuff. And look, if I select this square, I can paint it with any layer or erase it if I just use that. And here's a really neat thing, actually. If I do this and I paint it with NDiff. Okay, so if I say, yeah, I'm going to select all this, and now what is this? Well, it's NDiff. See down there? NDiff. Cool. Now, if I take this and make another little square, and I paint it with poly. Okay, what's that? Well, it's poly. And I can move it around here like these. Cool. But what happens if I stick it on the NDiff? Oh, look at this. Let's stick it here. This is a little weird. This pattern here. What's going on? Well, if now I say what? I just made a MOSFET. Okay, that's pretty neat. Another thing is you can root around. Basically, you can paint these squares like I've been doing, or you can root around and then you can change layers like this. Now I'm up to metal 2. Now I'm up to metal 3, and then I'll go down to up to metal 4, down to metal 3. Okay, so you can do stuff like that. And basically, what you're doing all the time is painting these little squares. So let's get rid of all of this and just bring in the mixer, because I don't want to draw these MOSFETs by hand. So to do that, I'm going to go back to xschem and say, okay, look, I need you to give me a netlist, but I want it to be special. I want it to be set up for LVS. So that way, everything in here, whatever that is and how many levels there are, will be wrapped up in one big subcircuit. So all I have to do is export this, boop. And now if you go and check simulation, got this mixer spice here. And if we look in, well, nothing too complicated, but it's what we want. It's our 4 ports and it's those 2 MOSFETs, and there we go. Everything is wired up. I can import this into Magic. So let's do that. So all I have to do really is say File, Import Spice, and go get that file. Boop. Oh, look at that. What is this? This is a MOSFET. This is a MOSFET. Now, Magic was nice enough to give me my ports here. So these are things that I can wire up and send to the right place. But what's interesting is that this is a MOSFET. Look at it. It is. Okay. Well, this is the gate. Okay. And it's got little errors here because this square is actually too small, but it'll be fine when we wire it up. The point is this. Here's the gate, and here's the gate. It's the same gate, and that's the channel here between drain and source. Now, which is which? It's completely symmetric. So whichever one is the drain and whichever one is the source is up to you. So all we have to do now is place these things. I'm going to undo this. Is take this and put it somewhere, and take this and put it somewhere, and wire things up. So the output goes somewhere here, let's say, and the LO will be here somewhere, and I want to tie it to the 2 gates. The RF I'm going to stick here, and the VSS I'm going to stick down here or something. So all I have to do is come in here and draw little squares. So if I wanted to, let's not be in that mode. If I wanted to draw a little square here, I would select this, and then I can just, oh, here's some M1. I'm going to copy that over. All right. And then I can take that little rectangle and move it here and do it again and wire this up. Whoop. Now, if I have this, it tells me. I have a way of knowing what's connected to what, so I can select this metal, and it says all these things are now connected together. Cool. As you can see, the DRC actually went down. So let's get rid of that. Let's do this again on this side. And what I'm going to do now is the same thing. I'm just going to connect the RF side. Now, these 2 metals are unhappy because they're too close, but we don't actually care because we're all going to connect this all up together very soon. Like this. Okay. And now I just want to paint this so that it's all connected. Like this. Oops. Unhappy. Unhappy, unhappy. Move this back a little. Okay. Boop, boop, boop. Now the RF gate's connected. Okay, so I'm going to wire this up. Okay, I've got her all wired up. You can see the LO is connected to these 2 gates, the RF to this gate, and the I out to this side, and VSS goes to the appropriate side of this MOSFET and to these guard rings.
Now, an important step at this point is LVS, layout versus schematic. The fact that drain and source are symmetric and basically up to you, and there's no help from Magic, no air wires, nothing to tell you what should be connected to what, that all means that it's easy to mess up here. But there's a tool, NetGen, that lets you do layout v schematic, and that is really good at figuring out if you got it right or not. Unfortunately, it's not that good at telling you what the exact problem is, but it does help a lot. I'll cover that in a Magic specific video soon. Here the circuit is simple enough that I just know I got it right. Now, once you have your layout, there are parasitics everywhere in there. Mostly capacitance between the traces and the substrate, and between themselves, and internal resistance. Now, Magic is really good at figuring that out, and you can send it voodoo commands to get it to output spice with all those parasitics included. So what I'm going to do is sabotage this thing a little bit, and I'm going to add in some extra capacitance. So we can actually see the difference between the simulation, the pure thing, and something with parasitic extraction. Okay, so I made these giant things here. VSS is basically connected to a bunch of metal, and the I out is above one side of it, and the LO is above the other. So this should give us some decent capacitance here. If I want to do parasitic extraction, in essence, I have to do some voodoo. And so if I basically look at this, this is the voodoo. But the point is, I made it so that I can just do parax extract, and then wait a minute. Did I save this? I don't remember. What's happening? I out is just this. Okay, so parax extract. Froop. Yes, delete. Blah, blah. Okay, let's take a look at that. Look at this. Instead of just our two MOSFETs, we've got a bunch of junk. And so all this parasitic resistance, and importantly, these caps here. So between LO and VSS, suddenly we have 4 femtofarads, which isn't a lot, but here is a lot. And we should have another one. Where was it? I out and VSS. Oh, yeah. Oof. 8. Okay, so let's try that out. Okay, so I ran that. This is our old friend, the mixer, and this is the parasitic extraction. So once I run that, I get results now for the output and the output parasitic extraction. So I just moved it, shifted it down -1 here. I can look at any of the results, and they're pretty similar. But the point is, if you're down here, let's say, well, the difference isn't huge, but you can see the simulation and the parasitic extraction version are just not acting exactly the same. And that's the whole point. You want to know, okay, with all this stuff accounted for, how's it going to react? So that's how that works. Pretty neat. Okay, if we're happy with that, time to stick it into the pad ring. Tiny Tapeout has a few options for this. I'm just going to take the smallest one. Okay, I got this def file here with interesting stuff in it from the Tiny Tapeout repository. So what I'm going to do is start up Magic and give it some bogus project name. So ttum myproject.mag. Now that doesn't exist, but it'll give us a name for our top cell here, TTUM, my project. So from here, all I can do, what I need to do is basically read in that def. So TT block, blah, blah, blah. Okay, what has happened? Oh, look at that. We have something here. And we have another here and another here. Now these UA things are basically the analog pins. So that's where they need to be, to be able to connect to whatever the stuff is on top. Up here, way up here, now look at that. That is a big box. Let's see, how far is that? Wow. Okay, down to here. So this box is, let's see, 222 microns. So we've got that much space in here, and we need to place all our stuff. So if I want to add my cell, I'm just going to place instance and then get my mixer. Flip. Oh, look at that. Look how sad it is. This tiny thing in here, it's basically not even the size of the space between 2 pins. But let's move it. Let's move it over here. And let's look at what's inside. Okay, this is my horrible mixer. And so all you would need to do now is choose which pins go to where. So I'm going to say that the output, so you can come here. And I'll paint that with paint M1. Okay, now I can route that like these. Doop. Now we got to get up to metal 4 here. This was something that came up a lot. You can do it manual style, but see this little square? If I just use a script I wrote called via stack, and I'm going to call it, let's go to 4, and let's go in direction south. Okay, that wasn't super well calculated.
So back to the stack. All right, and now my output should be connected. You really should be connected, my friend. Metal 4. UA is now connected to the output. That was harder than it should have been. So what you do is you connect each pin, and that's pretty much it. Now, my project involved a bunch of little cells like this and a digital block. Now, if you wanted a mixed signal design, like for my IDC, then you create the digital side using methods I've described in previous videos with the open lane flow. The end result of that is a GDS file for all the logic. You can basically import that as a blob and stick it anywhere you like in your analog project. You wire it up as it needs to be, and after that, it's another round of doing LVS, extracting parasitics, testing the entire system. So let's take a look at that. This is my magic file that I ended up sending to TinyTapeout6. So you can see that, okay, so none of the subcells are actually loaded, which is actually great because you can tell what I had to do at the top level. So up here are the pins that are basically the digital I/O. Let me get rid of this grid because it slows things down. So these are the bidirectionals and blah, 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 and here are the inputs. And down at the bottom are the analog. So here's my analog block, and then it connects to the digital block. Now you can look at the digital block. Let's load it. Okay, and so what you see is basically I popped in this block, and it had a bunch of little connections here, these guys, coming out. And so what I had to do was say, okay, well, this bit goes to this part of the DAC. Let's load the DAC just to see it. This thing goes to the comparator, blah, blah, blah. So the other thing, other than the pins, is these fat rails here. So you need to supply power. So this is ground, and this is plus. It's, yeah, it's very, very connected. But the point is, power, ground, and all the pins, and then you're done. I mean, this block just is a thing. It's a cell that I can include. Let's go down into it. Cell down hierarchy. Bloop. It's just this that I import and then stick wherever I want. So up. So that's pretty much it. This is actually my capacitor, if you're curious. So I did a multiplicity 4 or something like that, and that's what it gave me, and I basically had to connect all that up. So you can see, let's see, I made these little shortcuts. This is layer 1 metal, layer 2, layer 3, and layer 4. Layer 5, no touchy. That's basically how power shows up. So anytime the power on layer 5 crosses one of these layer 4 powers, and it has the right name, so this would be V power, I think, and that one would be V ground. When it crosses any of these, V is a drop down, and you get power there. So you have this grid coming up from up top, and you don't have to worry too much about that. One thing I would have changed was would be to have put more bypass capacitance, because in this world, in the digital, basically where you're not filling anything, you get a whole bunch of bypass caps for free. The system takes care of it. In analog land, that's your problem. So yeah, next time, more of that. That's pretty much it on this front. When you've got a digital blob like that, you can simulate it entirely in analog land. This is hard, heavy, and slow, but it works the same way as the rest and shows you exactly how things will behave, parasitics and all. Otherwise, you can go the sensible route and leave the digital bits digital using Verilator. This requires more setup and messing around, but then it runs at a decent speed. The results I got from IADC were using an analog 5 MHz clock and accounting for all the parasitics, just because I at first had trouble getting Verilator to behave, but also because I was curious. Now it took 16 hours or something, but the results are beautiful to look at. When you're all set, you write out GDS and related files and get them processed through GitHub Actions that actually perform the additional checks. Now this bit me for a while, but I finally got the green check mark.
From there, the process is just to head to app.tinytapeout.com and make your submission. If you have a green light from GitHub, that part is completely pain-free. Now, I realize I zipped through a lot of the practical aspects of many steps. I also want to share tweaks and scripts that I've created along the way to make life better in analog world. So I'll be releasing at least xschem and magic related videos. So if you're still here, you may just be the right audience for that level of detail. Since you are still here, thanks. You are one of the very few I make these things for, so let me know which parts you liked or what you'd like to get more info on, and keep an eye out for upcoming videos. Have fun exploring the Tiny. I'll see you soon. Cheers.